Chapter 4, graphs of the circular functions. So now that we've been working with sine, cosine, tangent, etc., we want to now begin to look at what the graphs of those functions would look like if we plot their values. So as we can see, there's quite a lot in this section. We certainly won't get through all, looks like 39 slides here. But let's use the slides to also help us begin exploring graphs of these functions. And also I'll try to switch over to a graphing calculator from time to time as well. So graphs of the sine and cosine. First, we're going to take note of the fact that these are periodic functions. And the graph of sine function and the cosine function are very similar to each other. So we're going to look at those specifically. Then we're going to talk about techniques for graphing, things called amplitude, period. We have to define these things that help us talk about a graph. And so we're going to begin with the idea of what it means to be a periodic function. It says many things in daily life repeat with a predictable pattern, such as weather, tides, hours of daylight, lots of examples. Imagine a pendulum that just keeps repeating and doing the same thing. Tides, imagine a wave, kind of repeating waves hitting the side of a boat or something like that. This periodic graph represents a normal heartbeat. So periodic means that there's some period, typically of time or space, where after that period, you get repeated behavior. And so you could imagine on this graph that's showing here that have these sort of little squares, that after basically the first 5 squares, the graph just starts repeating itself and does the same thing again and again every 5 squares. And so periodic functions are basically functions that repeat, and they repeat over some period of time or on a graph or something like that. So you could, for example, imagine some pattern of the sun that repeats every day. And so the period would be every day. You could imagine, as we see, I don't know how many, what time was in this 5 square interval from left to right on this graph, but whatever amount of time that is, the heartbeat pattern was repeating in that period of time. So periodic functions that repeat over some period. That's the idea behind them. So they try to define that in a box, which is mathematically not super helpful. A periodic function is a function f such that the value of the function at x is exactly the same as the value of the function at x plus n times p, where p is some change in x over which the function repeats. And that's called the period of the function. So if x was like time, and you looked at the height of the water at 3 o'clock, and let's say the period was every 12 hours, well, then at 3 a.m., when you look at the height of the water, if you add 12 to that, then you'll get 3 p.m., you'll see the same height of the water, because the water may have gone down, but it comes back up and it repeats every 12 hours, something like that. So the idea here is that if you change where you're looking at the graph or what you're plugging into the function by some multiple of whatever the period is, then you're going to find that same place in the repeating behavior that you saw before. And so this is trying to show you that algebraically, even though I think the notation is confusing for most students. That's the idea. Oh, this is kind of overwriting here. It says the circumference of a unit circle is 2 pi. So the least possible value of p for which the sine and cosine functions repeat is 2 pi. And then it says, therefore, the sine and cosine functions are periodic functions with period 2 pi. And then they give you some statements about that. So looking at these is not very helpful directly. So what I'd like to do is switch over and let's just start looking at the graphs of these functions so that we can talk about these things while we are looking at the graph. And so to do that, I'm going to pull up a Desmos calculator for us, and let me share that. All right, so again, you can go to this just by going to the free online Desmos calculator. And so the way you can see the graph of any function on this calculator is by typing in y equals and then whatever function you want to have. So I'm going to put in y equals, and then let's just start with sine x. And let's just see what happens. So immediately it shows me this red wave here on this graph. And so they have some key points. You can see 0, 0. The thing to remember is that by default, this is set up with radians instead of degrees. And since the slide we were just looking at mentioned 2 pi, that's also talking about radians because we're talking about the circular functions in which we'll typically use radians. And so how much is 2 pi? Well, let's say I've just put that up here as a decimal. Let's say we do 2 times, and then where's my symbol here? There we go. 2 times pi. So that's about 6.3 if I round that off. So if we go onto this graph, you can take a look at where 6.3 is. That's right about there. And what you'll see is that the graph starts at 0, 0. It goes up in this bump here. It swings back down and it comes back to 0 here. And then it just repeats with that upward bump again. And so right here, where you've completed this cycle of going up and then down and back to the x-axis, that's one complete repetition of what the sine function does. And the value of 2 pi is right here where it finishes doing that and it starts over. So it goes up for this first bump, down below for a second bump that's below. And then when it starts repeating, it goes back to that first bump again. And it does that right around 6.3. So what people will usually do is they'll just look at that one cycle, that one period, that one range of values that repeats for the function, and then imagine that you could then just keep doing that to the right or to the left as the graph moved on. So that's how you can visualize what this period of 2 pi is for the sine function. Now, let's say we change this to cosine. So here's the cosine function. And so the cosine function really looks almost exactly the same as the sine function. The difference is, as we may recall, the sine is the y value of a point, and the cosine is the x value of the point as it rotates around the circle. So both of them are ranging between 1 and -1, but when you start with a 0 angle, then you're right there on the x-axis, then the x value of the point is 1, and cosine is the x value. And so that's why we're seeing that the cosine function starts at a 1, whereas the sine function started at 0, 0. But notice the 1 of the cosine function is right at the top of the same bump we saw in the sine function. The graphs are the same, one just is at a different place than the other. So if I imagine beginning the cosine function at the top of this bump when x is 0, and I start moving to the right, it descends down to 0. It goes to the bottom of the bump like the sine function did. It comes back to 0, and then it goes back up and reaches the top of the bump. And as I hover over it, you can even see it tells you that's at 2 pi. And so the top of the bump is where we started when we were at 0. So again, for the cosine function to go through its range of values and then start to repeat again, that also has a period of 2 pi. And so as we begin thinking about the sine and cosine graphs and the idea of having a period, I think the best thing to do is to look at the graphs while you're thinking about these things. Now, we can also go through the values that we know about for our primary functions. Let's hop back over as much as I can do that. to the slides again. I think I'm not sharing there yet. Give me a second to pull that off. So if I go back over to the slides, we can look at the actual values of the sine and cosine functions and imagine what's going on. So for example, when the plug-in to the sine function is between 0 to pi over 2, that's in that very first 90 degrees or in quadrant 1 on the unit circle. Well, the sine function is the y value of the point on the circle. And when you start on the x-axis, it starts at 0. And then as you go up through quadrant 1, it raises up to 1. So as they point out here, the sine function increases from 0 to 1. And you can see that on the graph that we just looked at, because the sine function started at the origin and then it went up to the top of the bump. And now we can imagine the top of the bump is when we're at the angle of pi over 2. Where similarly, the cosine function, which we just looked at, when we were at 0, it started at the top of the bump. And that's because the x value of the point starts at a 1 when you're on the x-axis. And then as you lift up from there on the unit circle and you go up to the y-axis, the x value goes from 1 down to 0. And we saw the cosine function on the graph at the top of the bump at the very start and then decrease down to 0 on the x-axis. And they trace this through each of the quadrants. So 0 to pi over 2 is quadrant 1. Pi over 2 to pi is quadrant 2. They're basically pointing out these things so that you will think about what the graph looks like and what it does in detail. So here's their nice render of this. And here we can see a couple of full cycles of the sine function. And so on their picture here, they went from negative 2 pi all the way up to positive 2 pi. And let's see, get the bottom of the table on there. And even though the graph does keep going beyond this range of values, they're just showing that part of it. So when I'm at negative 2 pi to positive up to 0, that's one range of 2 pi, and you see one full cycle of the sine function. And then from 0 to 2 pi is another full cycle of the sine function, because the period is 2 pi. So every time you go over 2 pi along the x-axis, you'll see one complete up and down cycle of the sine function. And they point out all of our common values that we've been working with when evaluating the sine function. Sine of 0 is 0, pi over 6 is 1/2, pi over 4 is root 2 over 2, etc. And then when you get up to pi over 2, you're up to 1. Well, these values on our table that we've grown familiar with are exactly what caused the graph to start at 0, 0, and then to rise up to the top of that first bump and get to the top of the first bump when you're at pi over 2, as the values get bigger and bigger and bigger and max out at a 1. And then from there, they shrink back down to 0. They go down to -1 as the y value goes down below the x-axis on the bottom half of the unit circle, and then back to where they started. They're showing a little window here of what it would look like to make a graph on like a Texas Instrument or some other kind of graphing calculator. But as we saw, you can also do that easily in Desmos. So they're trying to guide us with a discussion here. Again, the slide isn't really made in a nice, complete way. They begin to talk about the properties of the graph a little bit. One of the properties is called symmetry with respect to the origin, which they'll go into a better detail in the book. So I do recommend maybe reading into that a little bit more in the book than we have here. But the basic idea that they're showing here algebraically is that if I change the sign of the input that I'm plugging into the sine function, all that does is change the sign of the output. So sine of pi over 2, for example, well, maybe I'll show that up here on the graph. Here's an example of that. Sine of pi over 2 was 1. And if I change pi over 2 to negative pi over 2, then sine of negative pi over 2 is -1. And you can see that on the graph. So some of the things they're trying to sort of show algebraic here algebraically. We'll get used to that graphically and talk about it a little bit more then. But the basic thing we're trying to do is get used to the properties of the graph, what the graph looks like, things like that. This slide's a little incomplete. So there now, let's look at the domain and range a little bit. You may recall from algebra that when you have a function, you talk about the domain, which is all the possible numbers you can plug into the function. And that for our sine function, or now they're looking at cosine, for sine and for cosine, the domain is all real numbers from negative infinity to positive infinity. Because remember, the domain is a angle in radians on the unit circle that you rotate it around, and you can go positive numbers by going one direction, negative numbers by going the other direction, and you can circle around the circle as many times as you want, off to 1,000,000 or 1,000,000,000 or however far around you want to go. However, the range, which is the kind of values the function spits out after you've plugged in something into the function, the range of the answers we get for sine and cosine are always all between -1 and 1. And we discussed this a little bit before, but now that we're looking at the graphs, we can really think about and talk about this idea of domain and range. You're never going to get a value for sine or cosine that's bigger than a +1 or less than a -1. It'll always be between those two. And that's because, as we've defined, they're the x and y values of points on a unit circle. And all points on the unit circle are never farther away from the origin than 1. So they never have an x value that's bigger than 1, and they never have a y value that's bigger than 1, or correspondingly less than -1. But if we look at the cosine function, as we just did, and we could think about comparing it to what we saw on Desmos, you can compare the values that we know about cosine, like at 0, you have a 1, at pi/6, you have 3 pi/2, and they decrease down till you get to 0 when you're at pi/2. And then you can see the top of the graph is at 0, and then it falls down to 0 as the x value moves up to pi/2. So you can see these values, hopefully, and how they form this shape of this graph. So then similarly, they have a similar discussion about these properties, and they point out, for example, that for the cosine function, it's an even function, and that means that when you plug in the opposite angle, like the negative of x, that you get the exact same value as if you plugged in the positive value x. So it's hard to see that algebraically, but if we look at this here, the example that's easiest to use is that when you plug in pi, you get -1. That's right over here on the graph. When you're at pi, you have -1. Well, if I switch over to the other side and look at -pi, I get the exact same value. This type of symmetry, where the things on the right and the things on the left give you the exact same thing, we call that an even function, and that's called symmetric with respect to the y-axis. It basically, the y-axis down the middle, you can imagine that that's a mirror, and that what you see to the right of that is reflected as the same as what you see on the left. If you think of taking that graph and folding that piece of paper right down the y-axis, when you fold the two sides together, the two graphs would land right on top of each other because they're the same on the right and on the left of the y-axis. Again, we're trying to use this discussion and the graphs to sort of see properties of functions, what their graphs look like. They both have a period of 2 pi. They both have the same domain and range. All right, so now we're going to take a big step forward in considering these graphs. We're now going to modify the graph a little bit. And I'm going to take us back to Desmos shortly because that's the best place to do this kind of work. But we'll start with this slide where they're imagining us comparing what we would have for a graph of 2 times sine x compared to a graph of just sine x. So what happens if I take the sine x function values and I multiply them all by 2? You can see this on a table. Whatever values you would have gotten for sine x, you would just double those. And since y, the y value on the graph is the height of the graph, y is now equal to all the values that it used to be except doubled, then that causes the graph to go twice as high above the x-axis and twice as low below the x-axis because you doubled all the y values. It used to be the biggest x sine x would get is 1, but if I multiply that by 2, then it goes all the way up to a 2 instead of to a 1. And so they're showing how you could compare these and all the values get doubled when you simply take the function that you had before and multiply it by 2. Let's see how they progress with that. Yeah, they have a nice comparison here. And so in purple, you have the regular sine function, which tops out at 1 when you're at pi over 2 as an example. But if you're taking all those y values and multiplying them by 2, then instead of going up to a peak of 1, it climbs up higher and goes all the way up to a value of 2. And again, you could just imagine that you plugged in the value pi over 2 and that the sine function gave you a 1, but then you took that and you multiplied it by 2 so that y ended up being equal to 2. And in that way, maybe you can imagine how this top of the sine function bump gets lifted up from a 1 up to a 2 when you multiply all the values by 2. So they're going to create this category where they say these are examples where we're considering graphing things like y equals a times sine x, meaning some number a, like a 2 or a 5 or something like that. So they're going to multiply sine by a, and now we're going to define this thing called amplitude. So the amplitude of a periodic function is half the difference between the maximum and the minimum values. It describes the height of the graph both above and below a horizontal line passing through the middle of the graph. So again, this is a sort of general description of an idea, but if we look at it on this graph here, the basic idea is the center of this sine function, either with a 2 multiplied or not, is the x-axis. The graph is swinging above the x-axis, then below the x-axis, then above, then below. And so the amplitude is how far above the middle and below the middle that the graph goes. The original function from 0 went up to a 1 and got as high as 1 above the x-axis, and then swung down to a -1, getting 1 unit below the x-axis. So the amplitude of the original sine function would be 1. But when we multiply it by 2, then the bump got higher. So now we go from 0 up to 2. So now the amplitude is increased to 2. And we'll see that the amplitude is whatever number is sitting out in front of the sine x function. If there's no number written there, then it's an unwritten 1. But if you put a number there, then that's going to multiply the sine values and cause the sine to go up to that new higher level. And that's called the amplitude. So let's see, the slides are showing that pretty good so far. Let's see if they switch that to cosine or something next. So they point out, as I was just describing, that if you have a graph of y equals some number like a times sine x or times cosine of x, and a is not 0 because otherwise you just get a 0 times the whole function. You have the same shape as you would with the original function, except that now the range has been stretched up. Instead of going from -1 to +1, it now goes up to a and down to -a of whatever the amplitude is. So the a value in front here gives you the size of the bumps, basically. All right, so let's see. They're showing this again. All right, now they're going to the inside. All right, so let's take a look at that on Desmos. So again, I'm going to hop over. So what I can do here is I can just take this cosine function and leave it there for comparison, and then put in a new one where I've multiplied by 3 perhaps. And then we'll see this same effect, that when I put a 3 in front of the cosine, instead of the bump going up to 1, it now goes up to 3. And this range here from the middle all the way up to the top, or from the middle all the way down to the bottom, how far that is, that's the amplitude, and that'll be this number sitting out here. Now, one possibility which they didn't show specifically in the slides is I could put a minus number out front. And what you'll see is that turns the entire thing upside down, because now when I normally would have gone up to a positive value, because I'm now multiplying by a negative number, I now go down to a negative value. And where the graph used to be negative before, now it's positive, because negative times negative gives you positive. But the size of the 3, when I went to a negative 3, means the amplitude is the same. So the amplitude for a positive 3 or for a negative 3, the amplitude is basically the size of the gap from the middle to the top or to the bottom, and that's still 3. The amplitude will always be a positive number. It'll never be a negative number, even if the function is upside down, because we're really talking about how big does it swing up and down when it does, and that's just the size of this number out front. So questions about this idea of the number out front multiplying a trig function being something called the amplitude? So they could show you a graph of one of these trig functions and ask you to identify the amplitude. They could show you an equation like this, y equals -3 cosine x, and ask you to identify the amplitude. You could look at the graph and basically see, well, how far above the middle is the top of the bump? Or how far below the middle is the bottom of a bump? That's the amplitude. But the amplitude will always be the positive number of that space, that distance between the middle and the top or the bottom. And if you're looking at the function, as we just saw, you can look at the number that's multiplying by sine or cosine outside there, right in front of it, and then that'll tell you the amplitude. Okay, so this number sitting out in front, whether it's positive, whether it's negative, the absolute value of that number is the amplitude. And that's telling you how big the bumps go, basically, of the sine or the cosine. So now they're going to put a number in a different place. Now, instead of putting the number out front, outside of the sine function, they're saying, well, what if we put a number inside of the sine function multiplied by the x value? So we saw multiplying outside of the trig functions by a number causes the bumps to get bigger by that amount. Or similarly, I could make the bumps smaller by multiplying by something less than 1. Like I could multiply by a half, and then the bumps would get only half as big as they used to be. But what happens if I go inside and I multiply the angle inside of the function by 2 before the sine function has a chance to see it or evaluate it? So they show you could do this with a table of values. And what you'll see is that you reach the values you used to reach sooner than you would have before. Before, the sine function gets to the top of the bump when I get to pi over 2. And at pi over 2, the top of the sine function would be up at a 1. But now that happens at pi over 4. It happens sooner. And the reason is that we're doubling the angle before you're taking the sine of the angle. So now if I plug in a pi over 4 and I multiply it by 2, that then gives me pi over 2, and sine over pi over 2 is 1. So the 1 used to be over here at pi over 2, and now if you put in a 2 in here, it gets shifted over to happen at pi over 4. So that's a little confusing. You can see it here. Let's see if they show us graphically to make more sense of this. No, they changed the value and didn't show the graph. So let me switch back over to the graphs. I'm sure they'll show it at some point, but I'm going to go back because it's so much fun just bouncing back and forth between the two. All right, so now let's look at this green graph of -3 cosine x. And what if I just go in next to the x and I put a 2? Let's see what happens. Boom. And so what you'll see is now it fluctuates more quickly. I'm going to take the 2 out, and then I'm going to put the 2 in, And then I'm going to take it out, and then I'm going to put it in. And what you'll see is that basically the waves or the period of the sine or cosine function is now happening more quickly. So what happens is if I multiply the angle inside here by a 2 before the trig function acts on it, then that causes the graph to be generated twice as quickly. I'm basically doubling the speed at which the graph creates its period cycle. And so what that does is that shortens the period. If the period used to be 2 pi, now it's pi. If I go down, for example, and I look at this cosine function here with the red function, we can see at the top of the bump I'm at 0. And when I go to the top of the bump of the red, well, let's click on it. If I go to the top of the bump at 0, I'm at 0, 1. And then to get to the top of the bump again, I had to go over to 2 pi, 1. So there's the period of 2 pi. But if I look at this modified cosine where it's multiplied by 2 in here, the top of the bump here happens at pi over 2. And that's where we get 3. And then if I go over here, I get 3 pi over 2. Or maybe looking at the bottom of the bump would be easy. That happens at 0. And then I get back to the bottom of the bump over here at pi. So now it went through one full cycle and started to repeat after only a period of pi instead of a period of 2 pi. This will end up leading us to some kind of formula stuff. So for example, if I have a 2 in here, if I had a period of 2 pi before, if that was my period for the cosine function, then the way I modify that when the 2 is put inside here is I would divide that by 2. And now we see that with the 2 in there, my new period is just pi. And they'll show you this little formula in the materials. So now I'm going from 0 to pi, and I'm getting a complete cycle of the circle. Whereas before I had to go from 0 all the way over to 2 pi to make that happen. So now basically it's shrunk the graph in this direction. It squeezed the graph or compressed the graph down toward the y-axis so that the wave happens more quickly. It's reduced the period by dividing it by 2. Okay, so they're trying to show this on the table, but I think as I show you, it makes more sense on the graph. But they do kind of summarize here. They say, normally, if you had a period from 0 to 2 pi, take that and divide by whatever the b number is that you put inside next to the x. So if you have sine of b times x or cosine of b times x, whatever that number is on the inside next to the x, the period of 2 pi divided by that b, and you'll get your new period. So these values give the minimum points, the x-intercepts, and the maximum points on the graph. I was focusing on the top and the bottom of bumps because those are kind of the easiest ones to find, but all of the values will be sort of squished in from where they were before. All right, so looking here, it says, let's consider graphing one of these functions where you put in this b value next to the x, like graphing y equals sine of 2x, and compared to the graph of sine x, which I just did graphically. They didn't do it graphically, that's why they're discussing it here. But they're pointing out, well, instead of having a period of 2 pi, you would divide that by 2, as I just showed, and you would get a period of pi. And therefore, every period of pi, the graph would repeat its little up and down wave. So normally you'd have a starting point of 0, you'd have a finishing point of 2 pi. Well, now you could change those to a starting point of 0 and a right end point of pi, and all of your up and down bumps have been divided by 2 as well. Normally at pi over 2, you get the top of the bump, which is their first quarter point. But if I take pi over 2 and divide that by 2, I get pi over 4. Normally, the halfway point around the circle is pi, and that's normally when the sine function has come back down to 0. But now that midpoint will happen at pi divided by 2, etc. They kind of showed that with the table. And here they're comparing the two graphs as I was trying to do on Desmos. So the purple graph is regular y equals sine of x, and you get an up and down bump between 0 and 2 pi, one full cycle. But for sine of 2x, it completes that up and down bump just from 0 to pi. And if you go from pi to 2 pi, it just does it again. So now it's repeating every period of pi instead of 2 pi, which causes the bumps to happen twice as quickly and causes the graph to be condensed basically by a factor of 2. So there's kind of two things that are your starting points for looking at the shapes of these repeating trig functions that have a period. The first is the amplitude. That's basically the size of the peaks from the middle to the top or the middle to the bottom. That's the amplitude. And if you multiply by an a number outside of the trig function, that will inflate or deflate the amplitude, depending on if you're multiplying by a number bigger than 1 to make it bigger or a number less than 1 to make it smaller. Think of multiplying by 2 or multiplying by a half. And then we're also saying that you can multiply the input, the angle variable, by that number before the trig function acts on it. And that's when you're seeing this behavior here. And what happens is if I multiply by a 2 here, then the graph happens twice as quickly. And so you see the period actually shrink. So if you're multiplying by a 2, you divide the period by 2. If you're multiplying by a 5, you divide the period by 5. And it causes it to happen 5 times more quickly. These are the two things they're trying to introduce, is these multipliers. So focusing on the period, when b is a number greater than 0, that you multiply in there next to the angle x, the graph will resemble the normal graph, but the period will be reduced, or will be the old period of 2 pi divided by whatever that b number is. Same for cosine. So as an example, they could say, what is the period of the cosine of 2 over 3 times x function? And what you would do is take the period of 2 pi and divide by that number that's multiplied in front of the x. Now, dividing by 2/3 can be converted into multiplying by 3/2, the reciprocal. And then you'll see that that's 3 pi. So you used to have a period of 2 pi. Every 2 pi, the function would repeat. Now the function repeats every 3 pi. From 0 to 3 pi, it will repeat. And you can see that graphically. You could use a table of values, taking all the old values and multiplying them by 3/2 as they did here as an example. And then they're showing a little one period of this new amplified cosine function in which they multiplied by 2/3 net to x. And what you see, it goes from top of the bump down and back up to the top of the bump after 3 pi, because now 3 pi is the new period. So they put these things together and give you some guidelines for sketching graphs of trig functions yourself. Now, again, it is good to do some sketches of trig functions by hand a little bit, just to get an idea of what's going on, getting very, very used to these functions and their graphs. But at the same time, I do recommend you make liberal use of a graphing calculator as a tool so that you can quickly change and modify graphs and imagine what they look like. And if you sketch a graph yourself, you can quickly pull up the graph and see if it looks like what you sketched and if that makes sense to you. So this is a nice little table. And that's where we'll finish with this slideshow. And so the nice thing about Desmos here is that it's really just great for playing with graphs, right? I can quickly change the number out front to whatever I want. I can quickly change the number inside to whatever I want, maybe even 1 over 2. That's not what I wanted. Let's do this. So if I'm going to do something fancy, I'm going to make a parentheses here, and then I can do 1 over 2, I think. There we go. And let's say I make this a small number up front again. And so you can easily compare graphs, see where they go. Imagine multiplying the x value in here by a number that's small, like a half or a third or something less than 1. And then you can say, well, that's what happens when I multiply by little numbers. What if I change that to a 3? And you can just see how it's only changing things in the period direction along the x-axis. And then, of course, you can multiply things out front by small numbers or big numbers, like maybe 0.2, and I get a teeny little bumps. Or multiply that by 7, then I get tall bumps, etc. So having a tool that quickly plays with graphs nicely for you as you're trying to figure all these things out, I think is really helpful. Now, having said that, oh, I thought I had the homework up there still. Let's see if we can see what kind of problems are expected from you in the homework as you're trying to do this, which I just lost track of. So let me grab that back again. So they're giving us a function, y equals 2/3 cosine x, and it says to determine the amplitude of the function. And then also choose its graph. So I'm guessing after amplitude, it'll ask us to pick a graph. So what do you guys think? From our discussion, do you think you could figure out what the amplitude is in this case? Max is suggesting it's just the 2/3 that's sitting out front there. So as we were seeing, yeah, and Cameron agrees that basically whatever that number is outside of the function, that's going to change the height of the bumps up and down to whatever that number is. And that is the amplitude with a positive number. So I would just put 2/3, and there you go. But then they want us to pick the graph. So first of all, we want to remember what a cosine graph looks like, and then see the one that would make sense if the bumps had been changed to 2/3. Now, when they're showing you graphs to pick from, you can make them bigger or smaller, or if you click on one of these arrows, it'll just expand it up to the biggest that it can be, and then you can get kind of a closer look. So I would want to know what the cosine graph looks like, and if it was modified like this, how that would change it. But again, keep in mind, you could also just type this graph into your Desmos calculator and see what it shows you. In this case, I know the cosine function normally has its peak right at when x is 0. And so, for example, the top peak of B is not when x is 0. The top peak of A is not when x is 0. So it's got to be C or D. And then I want the peaks to go from up to 2/3 and down to 2/3. And it looks to me like that's D. So up here is where we're at 2/3. There's a 1 up there. So it looks to me like it's D. But again, you could also put that into Desmos and compare to what you got on Desmos as well. Questions, comments, discussions about this problem here?
So if it is cosine 2/3x, then the amplitude would be just 1.
Correct. Yeah, if you multiply inside by the x, that doesn't change the height of anything. That only changes the period. Does that make sense?
Yeah.
Good question. Other questions about anything on this example? All right, let's see if we can squeeze in one more of these in a couple minutes, maybe go up to number 12. So it says now they're doing two things: graph this function, give the period and the amplitude. So now they've multiplied by 4 on the sine function. So that's going to make the bumps 4 times bigger and smaller. But then they've also multiplied x by 1/2. So that's going to make the period happen 1/2 as quickly, meaning more slowly, and get stretched out. Now, you could just type this function on Desmos and compare the graphs on Desmos. But for example, I can see that this one doesn't start at 0, 0 like the sine function should. Neither does B. So it has to be either A or D. And the A function has been flipped upside down. So it's going down instead of going up. So I'm just looking at that. I think it's got to be D. Just from a quick thing. But again, you could type that in Desmos and compare directly to try to get used to the idea. Then the amplitude, as we saw before, is the number sitting out front, which is a 4, as long as it's positive. And then the period, I would take 2 pi and divide by 1/2. And if I do that, I actually get 4 pi, which I'll just do that for us quickly here, as we don't have a lot of time left. But there's another example of a problem from our homework.